Hello, welcome to Noise Control and its Management. Today is the 5th day of this particular week, which is the 9th week of this course. What we will cover today is the noise as it comes out of compressors. So, compressors are machines which have a function very similar to that of a pump. The difference is that pumps are used to increase the pressure in liquids, while compressors are used to increase pressures in gaseous fluids. And based on this particular fact itself, that compressors are used to increase pressure in gases, by virtue of their function they are extremely noisy machines. So, it is important that whenever we are trying to develop estimates on noise from noise in a room or outside, if there are compressors around, it should be very important that we do consider their presence while estimating the overall noise levels. Compared to compressors, pumps are a little less noisier, and compared to pumps, motors are even lesser noise making machines. But amongst the 4 machines which we have considered till so far, fans, compressors, pumps and motors are probably the least noisy, while fans and these compressors, they produce awful amount of noise. Let us talk about compressors. Okay. So, like pumps, compressors also have a stator and a rotor, and as the rotor moves past the stator, now stator has different slots and the rotor has different blades or projections, and as it passes through that, it generates a lot of puffs of air which gets pushed, and the frequency of this thing is, well, let us call it FB. So, what does FB mean? It means blade pass frequency. Okay, it means blade pass frequency. So, it is basically the number of puffs which a compressor generates as it is pushing out air. It pushes out air every second in so many number of steps. So, what is this number? This is equal to Nr times Ns times Nr. So, this is divided by Kr. And how do we get this relation? So, imagine, okay, so first we will define what are these terms. So, Nr is equal to number of rotors, or actually rotor blades, and then Ns is number of stator blades, and then Nr is not RPM, it is revolutions per second, and Kr equals greatest common factor of Nr and Ns. So, this is our relation, this is the blade pass frequency. Every second air or whatever gas is being compressed, it will be coming out of this compressor in these so many puffs, So, where is this relation coming from? So, let us try to understand this. because later when you develop deeper interest into noise control and management, a lot of noise can be resolved in terms of blade pass frequency and its higher order harmonics. So, consider just a simple so let us say this is the shaft and let us say there are 8 blades, 8 blades. So, the shaft is rotating and I have made a very simple picture and it is rotating. So, attached to the shaft are 8 blades, okay. And through these 8 blades, so whenever and these 8 blades are passing and as you rotate, so suppose it is rotating is like this. So, this is one blade number 1, this is blade number 2, then you have 2 blades here and then 4 blades are at 45-degree angles, and when it is rotating all these 8 blades are rotating, and in front of these 8 blades let us say there is one stationary blade. So, that is a stator blade. Suppose we just consider one stationary blade which is the stator blade and then these 8 blades are rotating. So, when this first blade passes, there is some air which gets compressed between this rotating blade and the first blade. So, then the second blade comes, then again you have a second interaction between the aerodynamic interaction between the stator blade and the rotor blade. Then the third blade comes, you have the third interaction. So, when the so if the so in one revolution how many interactions are there between the stator and the it will be 8 interactions. Now, suppose there are 2 stator blades. So, one blade is like this and another blade is on that side, then there will be 8 times 2 which is 16 interactions each revolution. So, that is why, so if there are NR and NS rotor blades and stator blades, the total number of interactions will be NR times NS. And if in each revolution, if in each second there are NR revolutions, the total number of interactions will be NR times NS times NR. But then there is a term in the denominator Kr, okay, which is the greatest common factor. So, consider this. So, why are we dividing it by Kr? So, to understand this, let us look at this picture again. So, suppose you have, let us say you have only 3 blades, you have only 3 blades. So, one is at 0 degrees, then the other one is at 120 degrees, the third one is 240, and then when they rotate every 100. So, you have 3 blades and you have, so 3 rotating blades and 1 stator blade. So, in each revolution the number of interactions with the stator blade will be 3, number of interactions will be 3. Now, you consider that instead of one stator blade there are 3 equally spaced stator blades also. So, when this guy interacts with one stator blade, the other blade is also interacting with the other stator blade, right. So, the interactions does not go up, number of interactions is not going up, okay. So, that because the greatest common factor between 3 stator blades and 3 rotor blades is 3. But suppose you had 3 rotor blades and 2 stator blades, then the number of, so with one stator blade there will be 3 interactions and the second set of interactions will happen at 180 degrees off, okay. So, in the first case NS is equal to 3, NR equals 3, and how do you find out the greatest common factor? NS is equal to 3 times 1 and NR is equal to 3 times 1. What is the greatest common factor? 3 is the greatest common factor. So, that is how. But if it was in second case, if it was NS and NR, let us say this is equal to 3 and this is equal to 5, then this is, so what is it? 3 times 1 and 5 times 1. What is the greatest common factor? 1. Huh? So, in that case Kr would be 1. So, that is the reason why we divide it by Kr. Okay. So, this is the blade pass frequency. This is extremely important parameter. A lot of rotating objects we are asked what is the blade pass frequency, because a lot of times the sound has a very strong tone. I mean the sound could be broadband plus tonal in nature, but a lot of times it has a very strong tone associated with this blade pass frequency. And this is not only true for compressors, it will be also true for all rotating machineries. Wherever we have blades and static objects and a moving object passes through a stationary objects, you will have this blade pass frequency tone come again and again. So, let us do one example very quickly. So, let us say we have a motor or a compressor, and it has 9 stator blades and NR equals 6, RPM equals 6000, then FB blade pass frequency, what is it? Okay. So, we have to first compute Kr. So, Kr, what are the factors of Ns? What are the factors of Ns? Factors of Ns, so 1 is 1 times 9, you can factorize it at, you can also factorize it as 3 times 3, and the third way you can factorize it as is 9 times 1. And for rotor, 6 times 1, 2 times 3, 3 times 2. So, this is all repeating, so I will not repeat it. So, these are 4 possible 4 factors for Ns, these are 4 factors for Nr. So, what is the greatest common factor? Greatest common factor, if you look at it, is 3. So, Kr equals 3. So, our FB equals 9 times 6 times, our RPM is 6000, but we have to multiply it by NR. NR is RPS in the, okay, RPS. So, 9 times 6 times, and the RPM is 6000. So, NR equals 6000 divided by 60. So, I get 100 divided by 3. So, I get 5400 by 3, which is 1800 hertz. Now, let us consider another case. Now, this could be an extreme case where Ns is equal to 36 and Nr equals 24 and RPM is still 6000, then what is FB? So, again we have to compute Kr, and just to recap, so how do we compute? So, Kr is equal to what? So, once again we factorize Ns in all possible ways, 1 times 36, 2 times 18, 3 times 12, 4 times 9, 6 times 6, and then if I go down then it just repeats. So, these are, and then for Nr, what are the factors? 1 times 24, 2 times 12, 3 times 8, 4 times 6, and everything else gets repeated. Okay. So, what is the greatest common factor? 12. Okay. So, Kr equals 12. So, Fb equals 36 times 24 times 100 divided by 12. So, I get 72 into 100, 7200. Okay. So, this is the blade pass frequency, but like in other situations, in other cases, as in case of fan, pump, motor, our basic interest is not to just find blade pass frequency, but also find the sound power level of the overall compressor. So, the question is LW, what is the value of LW, okay, for a compressor. Now, these compressors are of two types, and depending on what type of compressor we are using, the relationship for LW will change. So, the first one is centrifugal and the other type is axial. So, we have to know which compressor we are thinking of using. So, next I will write down the relations. LW equals 20 log 10 HP over HP 0 plus, so these are all empirical relations, U over U 0, and I will explain all these terms. So, this is for the centrifugal compressor. And if the compressor is axial, then it is 20 log 10 HP over HP 0 plus 76. Okay. This is for axial. So, this is HP 0. Okay. So, what is HP? HP is power used by compressor in horsepowers. HP 0 is a reference horsepower level and that is equal to 1 HP. Okay, it is equal to 1 HP. So, in the denominator we just put 1. U is called the blade tip speed. What does that mean? It means that, so in a centrifugal compressor you have all these rotors, they are basically blades and they are rotating at high speed. So, what is the speed of the tip of the blade as it rotates? Okay. So, if you know the RPM and if you know the diameter of the blade, then you can calculate the blade tip speed. So, this is in meters per second, and then U0 is the reference blade tip speed, and this is again in meters per second. And what is the reference blade tip speed? It is a strange number, and that is 243.8 meters per second, because the original computations they were done in foot pound system, foot pound second system. So, it comes to some good number in foot pound second system, but when you convert it into meters per second, this is the number 243.8 meters per second. So, that is there. Okay. The other thing to understand is that this noise from compressor is in general broadband. Okay, it is broadband in nature, but it is not necessarily that at all frequencies the sound power level will be the same for all octave bands. It is broadband with highest power level at frequency Fm. Now, this frequency Fm is different than the other frequency which we had talked about, which is blade pass frequency. This frequency Fm is different. So, if you look at the noise coming from a compressor in general, it will have all sorts of frequencies coming out in the noise, but one particular frequency will be the highest, and that frequency we call it as Fm, maximum frequency, frequency corresponding to maximum amplitude. And what is the value of that Fm? So, Fm equals 1000 times U divided by U0, where U is the blade tip speed in meters per second and U0 is reference speed. This is for centrifugal compressors. And if we have an axial compressor, then it is equal to 2 times number of blades times Nr. So, this is number of blades in first stage of compressor, because a lot of these axial compressors, they just don't do compression in one go. You have first stage where you go from some pressure to higher pressure, then you take that as the input and then again. So, they are multi-stage compressors. So, first number of blades in the first stage compressor, and this Nr is revolutions per second. So, I should write chota r, little r, okay, RPS. So, what I have explained to you is you can calculate for, so this is for axial. So, what you have learnt is how to compute sound power level for compressors, and there are two different relations, one for axial compressors, another one for centrifugal compressors, and this noise which comes out of compressors is typically broadband, but it has a maximum amplitude at particular frequency called Fm, and the value of that Fm is approximately can be computed by these two relations. Okay. So, that is what I wanted to discuss today. Tomorrow we will continue our discussions on compressor. We will also learn how to break this energy or this sound power level into different octave bands for the compressor, and then also we will do an example, so that we understand the problem of finding out LW from compressors in a better way. So, that closes our discussion for today, and I look forward to seeing you tomorrow. Thank you. Bye.